Hey, good morning, everybody. Well, first I got to say it's really exciting to be here. I was on what I believe is the first prescribed fire in Pennsylvania around at Lehigh Gap quite a while ago now, and it's really exciting to see this room full of people and all the acres that you guys get treated, and just how many folks are excited and interested, and just how quickly this program has grown. I think that's a real rock for the region where there's a lot of states that need to, burn more. And so it's exciting to be here today. I just wanted to start. I have like all kinds of things I'd love to talk about today. I'm going to try to hit a bunch of them. I work for the U.S. Forest Service. Okay. So I work for the U.S. Forest Service Northern Research Station, and the Northern Research Station is basically the same footprint as R9, and so that's the 20 northeastern states in the country. My research program is we've just broken out. We're the Climate, Fire, and Carbon Cycle Sciences Research Unit, and fire has broken out of that. Thank you. And so this is the footprint of where my research program represents for fire. And then, and this is my program that I'm a team leader of. Nick Skoronsky, some of you might know, he's a Pennsylvania resident. He's down at our Morgantown, West Virginia office. He's the project leader for our new physical and ecological fire processes and interactions applications research work unit. That's a long title there, but basically it's like all things fire. And so in addition to that, Nick and I both got started outside of the Forest Service with fire. He got started working on the military base, Joint Base Dix McGuire Lakehurst in natural resource management. I got started as a part-timer with New Jersey Forest Fire Service. And so both of us have also continued, while we've developed our primary research careers, we've also continued sort of moonlighting as with fire management agencies over the years. And before I get into the research part of the presentation, I really like that ICT4 presentation earlier. And, on the forefront of my mind is that, we had a big drought last year, and, it's raining outside right now, but in a lot of places we're still in a drought. A lot of the swamps, at least by where I live, there's no water in them. All the water holes are dry. You dig down a little bit and there's really not the moisture that we normally have in the forest. And I gave a presentation in September at the National Cohesive Strategy meeting in Atlantic City. And, I was asked the question, how are we going to be prepared for as things get really bad in the future? And I said, well, we don't have to really look ahead. You just look back. We had like catastrophic fires in the Northeast prior to the current times, and we've kind of been in an all right situation for a while. But historically, some of the worst catastrophic fire years where there were fatalities and things were preceded by years of multiple droughts, prolonged droughts, and where I can only think about folks being tired and everybody's got some other job. Most of us, like, we're not just waiting for a fire all day long, but that's a collateral duty. And so, you have like days on end that you're out on fires and you're like getting behind on everything else in your family. And so it's important to have that situational awareness up. And I bring that up. We've got a staff ride. I don't know. Has anybody ever been to a staff ride or heard of a staff ride before? So there's these staff rides around the country. Staff ride's kind of like an after action review for an incident that you weren't at. And there's staff rides for Yarnell Hill, or a staff ride. There's a staff ride for the Man Gulch fire. And we've been developing a staff ride in New Jersey. I'm not the lead of it. We've been helping a little bit. We've had a number of fatal fires in a pretty small area, the New Jersey Pine Barrens, Bass River area. And the most recent one was, a while ago, 1977. But it's a really interesting staff ride that's coming up, and we're your neighbors, so it might be interesting to take a look at that moving forward. We just did the alpha testing of it this past week with folks from around the region. And some of the observations of that were almost everybody who died, so 1936, 1943, 1954, 1977. Every single one of those fires involved somebody dying in or next to their vehicle. Like sometimes their lunch wasn't even burnt on the dashboard, but they died of some kind of heat exposure in their vehicle. Almost everybody who died was, I think, under the age of 25 or around 25. And so, some things that we can learn from that is that, those little red trucks or your trucks are green and white, but they're not, they might not save you. It doesn't take, all it takes is one thing going wrong in a bad spot. A lot of these guys also, thought they were saving the world, and that was the main mentality. But everybody was trying to protect something that didn't even get burned in the fire. Folks died, and the house that they were trying to protect didn't even need protection. And so, especially for new folks, keep that in your head that, nothing is really worth dying for, and you're, rely on yourself and your people, and just remember that your equipment can fail. But it's a really neat staff ride, and hopefully you'll all get the opportunity to look at it. So with that, I'll just move forward. This is our work unit. We're a mix of folks with a lot of different talents: meteorology, forestry, engineering, and other kinds of equipment design and implementation. And so collectively, we do a lot of experiments where I work. I'm the site manager, lead scientist for the Sias Little Experimental Forest. That's the oldest Forest Service fire research facility in the country that I'm aware of. We actually got started in 1929. And that building, not that one, but one of our buildings is actually the first building that was built by the Forest Service, at least for research in the region too. It's a little tiny, like 13 by 13. That was the field research laboratory in 1929. Now we do a lot of experiments out there with fire, looking at fuels, looking at fire effects, and especially looking at ways that we can do local research that's relevant elsewhere to create new tools and test them for folks. So there's kind of like these four legs of our stool, that's science, delivery, and leadership in fire. And so we have wild and fire applications, physical fire processes, and there we go. Physical fire science processes, the science of how fire behaves, moves in the forest, and ecological fire effects. And that all goes back to, science, delivery, and leadership. We don't do it all by ourselves. So we have 20 states. There's not even 20 of us in the unit that we're supposed to be responding to. And so we work with all kinds of groups. You might recognize Tall Timbers up there, or some of these other universities in the region. But we work a lot with other folks who have different skills and talents and resources that we don't have to collectively solve some of these problems. So one of the things, I put a bunch of QR codes up in here because it's a little bit of a smattering of all different stuff, and I figured folks might want to dive in the one part that they are most interested in. A lot of our work gets done now through something called the Eastern Innovation Landscape Network, and that's a partnership between the U.S. Forest Service, Fish and Wildlife Service, and the Department of Defense, along with a lot of other partners: Los Alamos National Laboratory in New Mexico, the Ember Alliance. And this group is designed to facilitate and leverage long-term research investments in fire behavior, fire modeling, fire fuels, inventorying techniques. And in particular, in the Eastern United States, we have three main nodes: Fort Stewart, Liberty, and Joint Base Dix-McGuire Lakehurst. And so those are three places where there's been long-term committed fire research programs with fire management programs. And this has really served to enhance the connectivity between managers and scientists, so that we're not like, in two different silos, thinking of problems and conceiving them differently, but we're working together. And to facilitate that group has brought in, we actually have what we call the Incident Research Management Team. And so it's like an IMT for research. We brought in some of the best folks from other teams from around the country who help us coordinate events together where we can do fire research on operational burns. We're going to be going down to, we did a bunch of work at Fort Stewart previously. There's some burns coming up there. That's in Georgia. And we're going to be going down to Merritt Island and burning by Cape Canaveral at the Kennedy Space Center in April. And there's 76 researchers that are brought together to advance fire modeling and remote sensing research there. Issue here. Sorry.
My apologies. I think it has something to do with the virtual side. Anytime this bar moves,
Oh,
for some reason it's locking this up. So my apologies.
Okay.
I'll just do this, start again, and you should be good. Oh, no apologies necessary on your part. I just may have to advance back to.
Okay.
That's fine.
All right. So Innovation Landscape Network basically responds to the need for science innovation. A lot of the tools that we use, diameter tapes were invented like 150 years ago. And they're really great, but D tapes are getting kind of old. The fire management tools that for predictions that we have, what's in Behave, all that's based in 1960s research that really there's a lot of research to update it, but it hasn't been implemented very well. Fire is the most cost-effective, geographically impactful management tool that you can use. You can cover the most acreage with that. So we really need, tools to respond to these conditions. We also are acknowledging more novel conditions, bat habitat. What are the nuances of that we're trying to manage? What sort of nuanced fire do we need to apply to manage that situation? So we're working on developing tools that can help identify the conditions, monitor your management, and predict how ignitions and fire on different days can help you accomplish your management goals and really help you justify a lot of the work that from your experience is needed, but to help put some numbers to it. So I explained how we're working together with a bunch of different types of groups and researchers with different expertise coming together, because this is really a community problem across different geographies and disciplines. And this is kind of a busy model, or diagram, but basically what we're trying to do is leverage things like LiDAR, airborne LiDAR, terrestrial LiDAR, to develop better fuel models. So if you all have used Landsat, that's a little bit coarse. It doesn't capture all the heterogeneity. It's a two-dimensional data set, and we just spent the last half an hour talking about the importance of the three-dimensionality of forests for habitat and forage for the species we're managing for. We're trying to incorporate that into better spatially explicit, realistic fuel beds, that represent our fuels in 3 dimensions, and incorporate that into new fire behavior models that are based in physics that incorporate the complexities of ignition. So when you're out on a prescribed burn, you're not lighting like one dot and walking away and just watching that dot progress all day, or one line and just sitting there. You're lighting ignitions all day long to get the fire to do what you want it to do. And so there's a lot, you're leveraging those interactions, the physics of fire. And so there's new models that can estimate that better with the complexity of fuels. And there's a lot of work that we're doing to incorporate smoke predictions into that too. How local area smoke emissions will behave, as well as how that'll disperse over broader areas. So the backbone of this, I'd say right now, is terrestrial laser scanning. And that's a tool that is coming down the pike if it's not already in some of your shops. This is LiDAR is a lot of data points. I remember a couple years ago, I'd tell the folks in New Jersey, and they'd all kind of like laugh and glaze over when I mentioned LiDAR. There's new terrestrial laser scanners that I guarantee you can teach anybody in this room. You can teach your family members how to use it in about 10 or 15 minutes. It has one button. I don't want to oversimplify it to the extent that you'll know how to do everything with the data by then, but anybody can go out and collect the data very easily. And this is a great tool that can put identifying forest conditions right into the hands of a manager to put some numbers to it. So we have so you can, we're working on algorithms to pull out tree measurements from the scans. It works really well in southern pine forests that are burned a lot because they're structurally pretty simple. Running into some issues in the complexity of some of our northern forests, like where you've got coppice oaks that have been like cut, 3 times and they're growing all crooked and stuff. That gets a little more complicated. We're working on that, but there's a lot of metrics about the forest, and I'd encourage everybody to remember when you all took dendrology and you learned like all the names of the trees in the forest, so you could never look at the forest the same way. Like it was great in one way, but then on the other hand, you never could see like the forest the same way. Well, try to forget about like your D-tape and think about like if you've never measured the forest, all the ways that having all the points in the forest might enable you to characterize things besides the diameter or the height, but that structural diversity going through the forest. So we have all these groups have come together with USGS, and we have an online portal called Intellimon, and you can get to it from that QR code right there. That takes you to the main page that explains the program. But that's housed at the USGS Aeros Data Center, and you could go and set up a profile for your agency. It's probably already set up, actually, but where you could upload terrestrial LiDAR data to the cloud there. They'll archive it, they'll process it, and spit out a bunch of about 250 metrics about your forest. And those are all different statistical properties of the gappiness and the heterogeneity, the evenness in a scan. And it takes about 30 seconds to collect the scan. So for my staff, we can go out and scan about 150 plots in a 400-acre unit in a day, in an afternoon, where we used to spend like months doing forest census plots. This doesn't get you everything, but it's a really good descriptor of what's going on out there. And kind of how this works is you've got somebody like this fellow in the orange shirt. That's the terrestrial laser scanner on a tripod. He's setting it up. He'll press the button, walk away from it, and before he can finish responding to the text from his wife or girlfriend, the thing's done and he's got to go back and move on to the next plot. And so then you'll have somebody who's a data manager who's going to take that data off of your sensor and upload it to the Intellimon program, and you'll get 3-dimensional point clouds that kind of look like this, not necessarily that color coding, but that can show you the structure of the forest, and you could put them side to side and compare, and then you could make decisions and inform your land management with that. There's a new tool that's called part of the Burn Pro 3D program. That link will take you there, where all these sites that you measure go up on the Intellimon map on that website, and you can click on them and extract the information you want. But if you go to this Burn Pro 3D link, you can also just virtually scan around in a plot. You can pick any plot and explore what that looks like. And it does, as you can see, those are tree diameter measurements that are on there. So it does predict tree diameters. In some ways, it works really well. I'm interested in bark because bark is the primary, on pines, is the primary source of embers. And we can actually see in a before and after scan, the diameter of the tree where the trunk was burnt a little bit actually gets smaller. So that's pretty cool. One of the applications of this to get into the 3D modeling of fire behavior and those spatially explicit landscape fuels is this Fast Fuels program. And that's being developed out of the Rocky Mountain Research Station with my colleague Russ Parsons. And Fast Fuels is like an on-ramp to a highway. So you've got all your data, and Fast Fuels can take that. Right now, it uses FIA data to predict fuels across the entire country. But moving forward, it's going to start as we develop more and more this terrestrial LiDAR data. It'll also use that to predict spatially explicit fuels around your area. So the more scans that there are, the better. It's kind of like crowdsourcing your idea of what fuels are like. And that is well on its way. This is kind of what it looks like. This is an idealized fuel layer that Russ made for presentations here. So yeah, like I said, right now it's from FIA. It's developing, and I'll show you how it's kind of developing more in a second here. You can get the actual, right now they'll also incorporate satellite imagery to try to get the actual positions of denser or taller fuels. This is a case study out, I think this is Montana, where they were 3D modeling fuels for a burn unit. That's the burn unit. And, ooh, I skipped. Sorry. So this is the burn unit. Here we go. And this is the fuel bed that they created for that burn unit. Those trees and patches are pretty much where they were supposed to be. And then started with, this isn't quite working, but basically it started with the ground layer, and then they simulated prescribed fire through there. So with the new quick fire tool, you can parameterize spatially explicit fuels. There's actually a drip torch painter. And so you can paint where you want your fire ignition line to be. You can say how fast you want it to go. You can say, we're going to light this and walk, light to the corner, and then we're going to wait until it goes in a little bit and light some more. And so that's a really cool tool just to look at how fire might behave under different conditions through a unit. I mentioned that, a lot of that imagery there of the fuel layer looks a little bit coarse still. And we're working on developing better understory and fuel particle estimates for those types of models. So when you're prescribed burning, most of what you're impacting, most of what's combusting is on the ground and in the first, meter or two of the forest. And so that's also the part that's most poorly represented by satellite data. It's obscured by trees that are in the way. It's like really the hardest thing to measure and the thing that we kind of gloss over the most. And so we're actually working, we have another type of LiDAR for the laboratory. It's a scan arm LiDAR. If any of you guys have been to the dentist lately, dentists are starting to get them. And instead of giving you x-rays and stuff, they'll like wave this little pen in your mouth and they'll have a three-dimensional model of your teeth. And so we can do that same approach with leaves and sticks and pine cones and all the materials that make up the fuel bed. And we're working on using that to better parameterize fuel layers for simulations. And what we found through a lot of laboratory work and field work is that, the complexity or the composition of those fuels, and I'll give a shout out to my friend Jesse Cry in the audience here. He's done a lot of work with fuels in Pennsylvania in the area, and the importance of that composition of different species of leaves, of how they've accumulated is really important for how they're going to combust later. So we're working on simulating that. And so just to kind of recap on that, we're trying to update a lot of things. We're not trying to make anything obsolete. A lot of these approaches can be integrated in with the existing frameworks. They're kind of modernizations. They're iterations of our existing tools for measuring fuels, for predicting fire. And, we're really excited. There's a couple different places that are testing them. I would say be a little patient. We don't have the answer for everything at all yet. Think about there's been 130 plus years of forest measurement science. We're like 5 years into this. So fortunately, science goes a little faster now. But we're still developing the science of the data and how to best leverage this going forward. So one way that we're applying this, I have a burn that I've been following from near the research station for a few years. And this is one way that I've looked at the data. So we can get these 250 different metrics, and it's what's the skewness of vegetation in your plot, what's the average location of canopy height, and the maximum location of canopy height. And sometimes it's kind of a lot. Like, how do you make sense of all this? So we have these 43 plots across a burn unit that I've been measuring for this is like multi-temporal scanning. And each of these dots, the bottom scale there, the x-axis, -1 to 4, represents what time period it was. So basically -1 is pre-fire, 0 is like the day after the fire, we scanned it, and then we've continued scanning for 4 growing seasons after it burned. And this fire was really neat because part of it, we're in the pitch pine barrens, so like parts of it just nuke and there's not a green thing left, and then they flourish. And then the other part of the burn really didn't burn that hot. And that was kind of a difference of just ignition patterns and things. And so we scanned all these random plots, and we're tracking them through time. And so the red line in each of these, and I'll say that the ones on the left, that's the whole unit. That's our random plots across the whole unit. And then these are 2 plots that I pulled out that kind of typify the grouping. And how that's organized is basically the hardest burn in the top left corner, and the wimpiest burn was in the bottom right corner. And what we see is 2 different trajectories for those plots. Everything can be grouped together by how hard it burned. The plots that burn the hardest are following one trajectory. The ones that burned pretty weak, and I'd say like I could call it a restoration burn versus a maintenance burn, kind of in the style that they happened. And so the ones that burn really hard, and I call that like a first entry, restoration burn, we really reduced the fuel, and you can see that that red line is not as high as it was even after 4 years. It's still much reduced. All those fuels are growing back in the mid-story. The canopies kind of got whacked pretty hard. We have a lot of rapid regrowth from the understory. And at this bottom plot is typical of a really light burn. And what we've seen is that by the end of 3 or 4 years, we've reaccumulated all the biomass that was there before pretty much, but it reallocated to different parts of the forest. So you can see that the green line represents, the green and blue lines represent low vegetation up to 2 meters, and mid-story 2 to 5 meters. Those got knocked down and stayed down in the lower intensity burn. And what you're seeing is like, you top kill stuff and it slowly falls down over years. But the canopy grew. And so in those plots, and this is what I've seen a lot of, where you hit the bottom, but not the top so far, and you give the competition, there's favorant to the canopy, and it outcompetes the shrubs a bit. And you create that gap in the forest. And so, I think this is just kind of a neat way that you could use this tool in monitoring. The distributions of those dots relate, at any given time relate to a condition, and your forest is constantly moving in and out of conditions, or ranges of conditions. And so for bat habitat, for instance, without even burning, you might be able to go out and scan a bunch of forests that are quality bat habitat and see where they line up with management, and at what phases of management your areas are passing in and out of that condition that you're trying to get, to help kind of tailor your burning interval, or at least justify, if you already know you're doing the right thing, to justify it better. And so, yeah, this is just kind of a recap on that. Another thing I want to mention is I didn't put anything in here because I work in pine forest primarily, and there's other folks in the Northern Research Station who work in more hardwood forests and hardwood silviculture with fire. I was reading a bunch of articles. I'd want to include some stuff about oak and hickory silviculture, but since it's not my thing, it took me a lot of reading to kind of read up on it, and I didn't really get any great slides. But I talked to some people when I was looking at was that they were sort of describing the importance of these different types of fire for favoring, oak or hickory regeneration versus maintenance of mature trees. And it seemed like from Connecticut all the way down to the Appalachians, there's a feeling that you've got to kill some mature trees to create, to also kill off your competition of maybe cherry and gums and whatnot, to create that condition for the seedlings. If that's the objective. If the objective is to maintain, a maturing oak forest, then maybe you don't want to burn it as hard, and you're just trying to keep those guys going a little bit longer. So again, that importance in, we heard it in the bat presentation, there's that importance in heterogeneity, or mixing up the forest. You need a little bit of everything, and you can also burn things different ways to get there. So this is from a study a few years ago that kind of relates to that, but we used LiDAR across the Pine Barrens to look at the structures that are present. And what we found is that a lot of the structures are very much tied to the fire history, whether it was a hot wildfire or a cool prescribed burn, and how many times really influences whether that's a short, compact scrub forest or it's a taller, park-like stand. And obviously there's other things that play into that, like insects, drought, and whatnot, but these patterns really played out. We went from there, and Nick and my friend Engel of Puma worked on a project where they tagged a golden eagle, and they looked at where this golden eagle, how it was behaving in the Pine Barrens, and they came to find out that it was it liked to roost in the unburnt forest, but it spent most of its time foraging in the heavily burnt areas that were more open. So it's got like pretty big wingspan. And so he could cruise along through those open areas and see everything in there really easily. He was following the forage in there as well. And so it just was a neat case study of how wildlife uses these different structures for different parts of their life. There's a GTR that we just published last year about using terrestrial laser scanning. That was a big project with our partners at the Southern Research Station. And then I don't have time to get into it, but we do some other stuff too. And a cool highlight from last year was this embers video that we did. So we have a whole project on embers, firebrands. That's the #1 thing that sets houses on fires. Anytime somebody's entrapped by a spot fire, it's because, like, barring somebody lighting a fire in the wrong spot, it was an ember that set fire where they didn't expect to have one. So they're really important. Gifford Pinchot wrote about them in 1899, and they just haven't really made their way into any kind of management guideline or modeling tool. But as we've seen from recent events, they're really important. And we have been studying embers for a while. This video's pretty neat. So we'll do projects with New Jersey Forest Fire Service and the Department of Defense, where we'll burn out a catcher's mitt, and then we'll burn the next block over and ram it into there and catch all the embers downwind, and study how the fuel helped us predict what the embers were, how many there were, how far they went, and how things like, in a pine forest, if you proactively prescribe burning, you're actually reducing those bark flakes that comprise over 3/4 of the ember content. We also have done a bunch of work, and Jesse's been involved in this work. He's probably mad at me that we haven't published more of it yet, but we did a bunch of work on prescribed fire and ticks. That's another big issue. And getting back to that structural issue that we were talking about before, prescribed fire modifies that habitat that the ticks are living in, as well as other organisms. But prescribed fire really does reduce ticks. And we found in New Jersey, we haven't published it yet, but after 4 years, there was still a sustained reduction in ticks that we could measure. In the hardest burn plots and some annual burn plots, we saw reductions, and this is in forest, not grass. We saw reductions of anywhere from 50 to almost 100% in some of those heavily managed stands. So that's a really cool paper there in the link. And that's about all I got for today. But thanks for having me, and I hope we have any time for questions.